When you walk through a room, your body physically distorts the ambient Wi-Fi signals bouncing off the walls. By measuring those distortions, we can map human movement without a single camera. This is RuView, an open-source, research-grade radio frequency sensing pipeline. It is built for deploying custom spatial intelligence rather than acting as a plug-and-play consumer gadget. The foundation of this system relies on channel state information, or CSI. CSI measures how a wireless signal propagates from a transmitter to a receiver, capturing the specific scattering and fading caused by objects in the environment. Out of the box, extracting this data allows the system to detect human presence, quantify aggregate motion in a room, and track micro-movements like respiration rates. This is accomplished entirely through software and targeted microcontrollers reading radio waves. There are no optical lenses involved. Spatial intelligence is no longer restricted to the optical domain. Human presence leaves a deterministic, measurable footprint on the surrounding RF fields. Intercepting these RF fields introduces a primary engineering challenge. Capturing raw signals generates an unsustainable volume of data. This diagram illustrates the data density. A single frame of unprocessed in-phase and quadrature, or IQ data, payloads weigh in at approximately 11 kilobytes. Transmitting that 11 kilobyte payload across a standard wireless network at high frequencies congests the pipe, leading to packet loss and dropped frames. If you attempt to scale that architecture by adding multiple nodes to form a mesh, the local network bandwidth collapses under the compounding latency. Solving this bottleneck requires a shift in where the computation actually happens. Real-time spatial sensing depends on managing high data throughput and network latency. To manage this throughput, we begin at the edge of the pipeline, the physical antenna receiving the Wi-Fi signal. This antenna must run in promiscuous mode to passively intercept ambient Wi-Fi management frames instead of standard network traffic. To execute the necessary digital signal processing workload directly on the antenna, the pipeline requires the ESP32-S3 microcontroller. Older hardware models, like the original ESP32 or the ESP32-C3, are incompatible with this architecture. Those legacy chips lack the single-core compute performance necessary to process high-frequency CSI data streams on the device itself. Despite these requirements, S3 nodes can be built for a fraction of the cost of traditional optical camera setups. High-fidelity CSI extraction relies on having that processing overhead at the absolute edge of the network. Once the ESP32-S3 captures the frame, it runs an on-device feature extraction phase powered by the Espressive DSP library. This phase applies a fast Fourier transform, or FFT. As this diagram shows, the FFT translates the heavy, raw IQ data, separating it into distinct amplitude, phase, and spectral frequency bands. This mathematical transformation compresses the data at the source. The 11 kilobyte raw frame is reduced to a uniform 470 byte binary packet. Inside that 470 byte packet, the system retains only the essential variables: the magic header, node ID, RSSI signal strength, and the extracted CSI data. The process discards high bandwidth noise while preserving the deterministic spatial footprint. Shifting the signal processing directly onto the antenna node makes high-frequency wireless transmission mathematically viable. This topology map illustrates the next phase, moving that 470 byte frame from the ESP32 node to a central host aggregator. The transport mechanism is a continuous UDP stream on port 5005, pulsing at roughly 20 frames per second. Limiting the payload to 470 bytes allows the network to support multiple nodes operating simultaneously without collision. This architecture allows us to expand the system into a full ESP32 multi-node mesh. A strict architectural rule governs this mesh. Signal-level fusion does not occur over the network. The host aggregator collects these independent streams in parallel. This lightweight UDP architecture allows for scaling spatial resolution by adding more nodes without overwhelming the host network's bandwidth. Once the UDP streams reach the host machine, they enter the aggregator block. This is where feature-level fusion, phase sanitization, and Doppler extraction occur. In the first iteration of RuView, this intensive computing workload ran on a Python-based pipeline. That legacy system has been replaced by a modern backend written entirely in Rust. This chart details the performance delta. The Rust pipeline executes the fusion processing 810 times faster than the original Python code. In absolute terms, the Rust backend executes the full pipeline in 18.47 microseconds, resulting in a throughput of 54,000 frames per second. Reducing the latency to the microsecond level provides the necessary processing headroom to run neural network inference on the fused data stream in real time. Because the entire host server environment is containerized via Docker, this processing block can be deployed consistently across any operating system. This bifurcated architecture, pairing compression at the edge with high-speed fusion at the host, enables the microsecond-level processing required for real-time sensing. With the streams fused and processed, the Rust aggregator broadcasts the final data over WebSockets to the client endpoint. This interface shows the visualization endpoint, a Three.js browser dashboard that renders the raw RF telemetry into a 3D spatial environment. Several baseline metrics function immediately upon boot. The dashboard reports binary presence detection, aggregate motion levels, and single quality measurements. However, these native features differ from the more advanced 17-keypoint DensePose skeleton tracking. Extracting anatomical pose from radio wave distortion is not a plug-and-play capability. To achieve reliable anatomical mapping, operators must train a custom neural network model mapped specifically to the unique RF reflections of their own physical environment. RuView provides a deterministic, mathematically grounded foundation for RF intelligence. It leaves advanced anatomical mapping to custom, downstream software implementations. If deploying dedicated hardware isn't an option, the platform offers a fallback called commodity Wi-Fi mode. This mode relies on standard Linux Wi-Fi metrics, extracting data from basic RSSI readings and noise floors using everyday network interface cards. This approach involves a significant capability trade-off. Commodity mode can detect coarse motion and room-level presence, but lacks the resolution to track respiration or body pose. Unlocking high-fidelity spatial resolution requires the dedicated ESP32S3 CSI mesh architecture we've detailed today. That architecture dictates a specific journey for the data, starting as a distorted RF wave, compressed via FFT at the edge, streamed over UDP, fused in microseconds by Rust, and visualized through WebSockets. Real-time camera-free spatial sensing relies on local signal processing and optimized data fusion.